Welcome back. So, we will continue the discussion in the previous class on stability analysis of nonlinear autonomous systems. And last time we saw that at the hyperbolic equilibrium points, the linear stability analysis implies the nonlinear stability analysis. So, we may now concentrate on non-hyperbolic equilibrium points, and this will be handled by the use of Lyapunov function. It is a very simple tool, but very powerful tool as we see it. So, before I go into the details, so let me just mention a reference, Takashi Kanemaru, there is a nice write up by Takashi Kanemaru on Duffing and Van der Waals oscillators. So, this is available on the web. It is Scholarpedia .org. So, you can get much more information on this Duffing and Van der Waals oscillators. Last time we discussed little bit about that. So, you can refer to this write up by Takashi Kanemaru. Okay. So, now we move on. So, we introduce the Lyapunov function. Okay. Definition is very simple, it is not. So, again consider the autonomous system x dot equal to f x. So, this is our standard system. So, system and let x bar be an isolated equilibrium point. So, again we will be studying the stability of orbits of this system around this equilibrium point. So, we may assume, so this is our, hereafter we do this just for some simplification in writing, we may assume that x bar equal to 0. This we can always achieve by translating this system into a neighborhood of x bar. Okay. So, you can just check that. So, that is not this is no general, the loss of generality. Okay. So, just stick to this thing and let omega be a neighborhood NBD, neighborhood of 0 which does not contain any other equilibrium point of 1. So, this is possible because we are assuming 0 is isolated. So, a function, so this is a definition, a function So, all our analysis now is restricted to that neighborhood omega. So, we define functions and other objects on that omega. So, V from omega to r. So, a real valued function defined on that neighborhood of the origin omega is called positive definite respectively negative definite. So, any real valued function defined on omega respectively negative definite. So, this is definition. If Vx is positive respectively Vx negative for all x in omega and x not 0 and V of 0 is 0. Okay. So, this is, so I am not putting any other restrictions like continuity and other things, that those things will come as you go on. So, this is a real valued function which takes only positive values except at the 0 or negative value if it is negative definite. Okay. So, now definition of the Lyapunov function. So, this is very useful tool and it has been even adopted in other situations. Okay. A function V from omega to r which is C1. So, it is continuous, differentiable and derivative is also continuous, all partial derivatives is called a Lyapunov function for the system 1. Okay. So, that is where the system now enters, otherwise just it is a real valued function, right. So, what is the connection with 1? If, okay, so two conditions, let me write 1, V is positive definite in omega. So, that is the previous definition. And second one, that is connection with the system 1. So, del V dot f. So, del V is gradient of V. So, this is by definition. So, this is f is coming from the system. So, this is nothing but del V by del x1 into f1 plus etc. So, we are in n dimensional situation. So, remember V is a function from omega to r. So, it is a function of n variables. Okay. So, now this is a real valued function, okay, for all x in omega. So, this is less than or equal to 0 in omega. So, at all points in omega we require that this gradient V dot f. Okay. So, this is scalar product and that is what I am defining. So, this is a vector and f is also a vector. Okay. Grad V is a vector. So, this is the vector del V by del x1 etc. del V by del xn and f is the vector f1 f2 fn. So, I am taking the scalar product of those two vectors at every point in omega and we require that this is less than or equal to 0. Okay. So, that is where the given function is related to the system via the second condition. So, now theorem. So, these concepts were introduced by Lyapunov. This is stability theorem. So, suppose the system 1 possesses a Lyapunov function. Then 0 is stable. Okay. So, remember again by our notation 0 is an equilibrium point of 1, and so if as and when the system 1 possesses a Lyapunov function, 0 is stable. If in addition, so now we strengthen little bit the second condition, grad v dot f. So, again look at the definition, grad v dot f. So, that is again a function defined on omega to the real number. So, this is a real valued function defined on omega. I want this is negative definite. In omega, then 0 is asymptotically stable. So, now you clearly see what role the Lyapunov function plays as far as stability and asymptotic stability of any equilibrium point of the given system plays. Okay. So, that is the importance of Lyapunov function, and proofs are very easy and they use simple calculus. Okay. It is not very deep analysis, but you can already see the interplay between analysis and the differential equation. So, I have stressed this point again and again at many situations, and here is another situation where you see that interplay very clearly. Okay. So, proof. So, again you go back to the definition of stability and asymptotic stability. I will not recall that here. Okay. So, so consider the sphere. So, this is in n dimension sphere set of all x in omega. Okay. Mod x is equal to epsilon. Okay. So, let me just let me put set of all x, and since omega is a neighborhood of the origin, so I can choose small epsilon such that this is in omega for some epsilon positive. Okay. So, so to speak, so here is a simple diagram. Okay, I will put omega here, and this is the origin. So, I am putting this bar here. Okay. So, we will be working in that particular neighborhood. Okay. So, V being continuous, will have a positive minimum. This is the, because V is positive definite, by definition we will have a positive minimum So, let me call this S epsilon, some notation on S epsilon. Okay. Call it M. So, M is positive and it is the minimum. So, this is S epsilon. Okay. So, again by continuity, again since V 0 is 0, V is continuous. So, we can choose delta positive and delta less than or equal to epsilon, such that V is strictly less than M on S delta. So, let me again stress this thing. What does this mean? So, this means that is V of x is strictly less than x for all mod x equal to delta. Okay. So, let us go back to the previous page. So, delta will be somewhere here. Okay. So, this is delta and I am choosing delta so that the V will be strictly less than, and remember M is the minimum of V on the bigger sphere mod x equal to epsilon. Okay. Now pick any x 0 such that mod x 0 is strictly less than delta, and so you start your orbit and consider a solution x t of 1 our system with x 0 equal to x 0. So, I am now starting the orbit in the ball of radius delta, and we would like to show that this orbit through x 0 remains within x epsilon, and that proves the stability. So, wish to show so the positive orbit, okay, orbit is contained in mod x less than or equal to epsilon, and this proves stability. Okay. So, implicitly I am assuming that the solution x t of 1 with x 0 equal to x 0 exists for all t positive. Okay. So, this is a standard assumption that I have been telling. So, then we would like to show that the positive orbit. So, this is, remember, positive orbit through x 0. Okay. So, that we would like to show. So, once we show that thing, that is prove the stability. Okay. For this thing, consider V of x t. So, now we are bringing in the and V of. So, you compose the solution x with this real valued function V, the Lyapunov function V. So, you get another a function from the real line into the real line. So, that is the composition of V and x, and this by fundamental theorem of calculus, one variable calculus. So, this is 0 to t d by ds of. So, this you have already seen many times. Okay. I am just applying that. So, this is fundamental theorem of calculus. So, remember this. So, just you see how simple things in calculus are utilized. Okay. Now, the second hypothesis come into picture. So, by chain rule, okay, so this is another thing from calculus. So, d by dt of v of x t is nothing but dv by dx1 x1 dot plus dv by dx2 x2 dot plus etcetera plus dv by dxn xn dot. But remember, x is a solution of system 1. So, this is nothing but dv by dx1 f1 plus dv by dx2 f2 etc. And this is f, and this is nothing but del v dot f. That is what we defined, and by our assumption this is less than or equal to 0 in omega by condition 2. Okay. So, now if you put back this so remember, in the integrand we have this expression, and now by chain rule I have computed this one and shown that is less than or equal to 0, and again now you go back. So, here you see in the integrand I have that derivative. So, that will be, so therefore, v of x t minus v of x 0 is less than or equal to 0 by that integral, or so this is v of x t is less than or equal to v of x 0, and remember x 0 is chosen within that ball of radius delta, and by our choice this is less than m, and this is minimum on the sphere mod x less than or equal to m, and that proves that mod x t is less than or equal to m epsilon for all t, and that completes the proof. Okay. So, that so stability is one part. So, stability is easier. So, now let us go to the second part. Okay. Second part. So, we have the additional assumption. So, we have grad v dot f is negative definite. In omega. So, again let me stress, so that is grad v dot f at any point x is less than 0 in omega minus 0, and at 0 it is 0. At 0 is 0. Okay. So, this is important. this is we are going to use now. So, again from the first part, from the previous discussion, we see that this function, this composite function v of x t, a function as a function of t, is non-increasing. So, again you can just use that fundamental theorem of calculus. You integrate between any any two times t 1 t 2, t 2 bigger than t 1, and you see that that is in non increasing. So, that is v of x of t 2 is less than or equal to v of x t 1 for all t 2 bigger than t 1 bigger than or equal to 0. So, we are just concentrating on that positive orbit where this composite function is non increasing and it is bounded below, the function is bounded below. Why bounded below? Because that is our assumption, it is bigger than or equal to 0. Okay. So, here we have a non increasing function which is bounded below, and by calculus lemma this limit v of x t as t tends to infinity exists. Okay. So, here I have a non increasing function v of x t which is bounded below, that is why this limit exists. And since this is a non negative function, okay, call the limit equal to L. So, obviously L is bigger than or equal to 0. Okay. So, we used to show that L equal to 0. So, if L equal to 0, you immediately see that since V 0 is 0 and V vanishes only at 0. Okay. So, if we show L equal to 0, it follows that limit x t as t tends to infinity should be 0. Otherwise, if this limit is different from 0, then you go back here. So, limit of as t tends to infinity of v of x t will be v of this limit, whatever that limit, and that we are if we are going to show that that is going to be 0, then that will get a contradiction. Okay. So, this is important. So, once we show that the limit, this limit L is 0, it follows automatically that this limit of x t is 0, otherwise we get a contradiction. Okay. So, assume to get a contradiction, assume L is positive. Okay. So, again using continuity, of V and V 0 equal to 0. So, these are simple arguments, you should check them using your knowledge of calculus. We can choose eta less than or equal to delta such that V of x will be strictly less than L for mod x less than or equal to eta. So, here is the picture. So, we have this big, let me again recall that. So, this is epsilon. So, this is origin and we have a delta here inside, and now I am going to choose. So, maybe let me just and remember this excuse me, this eta is chosen so that we have this condition. Okay. This I can do because I am assuming L is positive, and we will show how we get a contradiction on that. And now you consider this x t, consider the orbit, positive orbit starting at x 0, and now I take mod x 0 less than or equal to eta, and which is automatically in that delta. So, that is no problem. Okay. And by assumption, okay, consider this thing, by assumption and this construction, you see that then O plus x 0, the entire orbit is contained in mod x less than or equal to epsilon. So, this comes from stability. So, this is part 1. So, no problem. And now, the second part, this set of all x I want to show that it is bigger than equal to. Okay. So, what I am claiming is the orbit lies in this green thing. Okay. So, it will not go to 0. Okay. And this part follows from that V of x t converges to L. Okay. So, it cannot go beyond it. So, the entire orbit lies in this annulus. So, therefore, O of x 0 lies in the shaded annulus. Okay. So, follow this geometry. Annulus. Okay. So, now we use the second hypothesis now. Okay. So, on the annulus, so that is a compact set on the annulus. What is the annulus? So, eta less than or equal to mod x less than or equal to epsilon, it is closed and bounded annulus. So, that is compact set. The function, so this is the second assumption, grad v dot f is negative and attains its maximum. its maximum. So, I want to put a notation for that. Okay, so, let minus k. So, since it is negative, this is negative. So, I just put maximum of grad v dot f at x, and x I am taking only on this. So, that is a continuous function, and this is a compact set. So, it will have a maximum, and since it is negative, so this is k is strictly positive. And now, go back to the equation which is given by the fundamental theorem of calculus, then v of x t minus v of x 0 is equal to 0 to t d by ds of v of x s ds, and this we have already computed. This is del v dot f x, and now I know that this orbit remains only in this thing. So, this is just less than or equal to minus k t. Okay. So, this is where I am using this definition of k, and x, the orbit is restricted to only this annulus. Okay. So, all these facts are used here, and this I am replacing it by its maximum, which is minus k, and the integral 0 to t ds is just t. Okay. So, therefore, so remember this is k is positive. Okay. So, as t becomes large, so this is a negative number. So, I can always exceed this x 0. So, if t is large, v of x t will be negative, and that is a contradiction, because v is a positive definite function. So, this contradiction proves to z equal to 0, and therefore, 0 is asymptotically stable. Okay. So, Lyapunov also has a theorem for the instability result. So, let me just state that also. So, theorem instability. Okay. So, suppose a C1 function. So, this is Lyapunov function, if you want to call it, for the instability case. A C1 function v from omega to r satisfies the following. Satisfies 1, in every neighborhood, every ball, okay, every neighborhood of 0, there exists a point where v is positive. Okay. So, I am not requiring v to be positive in entire neighborhood, but in every neighborhood there is a point. So, just let me again call it. So, every neighborhood, so there is some point, call it x. So, where v x is positive. Okay. I am not requiring that v to be positive everywhere in that neighborhood. Okay. And the second condition, that again connecting the function with the system, our system is positive definite. So, later on we will see that this condition we do not require no, we do not require this positive definiteness everywhere. We require this positive definiteness only when in the region where V is positive, then 0 is unstable. Okay. So, remark, so I will just write that whatever I said now. Condition 2 is required only in the regions where V is positive. So, this was observed by Chetov. Okay. Russian names, so I might have misspelled it, but this is okay. And there are other as far as instability results are concerned, there are more relaxed conditions given by others. So, this is sufficient for many purposes. Okay. So, let me sketch a proof of this thing and we will consider the examples next time. So, sketch. Okay. So, again the starting point is the fundamental theorem of calculus. Okay. So, d by ds of V of x s ds, and this we have already seen that this is del v dot f evaluated at x s. Okay, that's fine. And now you see this, our assumption is that this is non-negative. So, that means now V will be increasing. Okay. So, that is the idea. So, I am just sketching it, and you start a solution where this is positive. Okay. So, that means if I start at a point where V is positive, then I remain always bigger than that by this. So, this is an important thing for us. Okay. So, let me just sketch it. So, again you start with, so fix one ball, fix this x such that mod x less than or equal to epsilon, and this is in our omega. Okay. So, this omega there, and this is x epsilon, and now I take another one delta here. Okay. So, by hypothesis, so choose x 0 such that mod x 0 is less than delta and V of x 0 is positive, and this is possible by our assumption on V. Okay. So, in any neighborhood there is a point where V is positive. So, this is the condition 1. Okay. Start the orbit at x 0. So, that is, so this same thing as saying, so so let x t be the solution of our system 1 of 1 with x 0 equal to x 0. Okay. So, then by hypothesis, second hypothesis. So, therefore, by the integral fundamental theorem of integral calculus and the assumption, we see that this is bigger than or equal to v of x 0. So, this is v of x 0 and call this c, and this is positive. Okay. So, this is true for all t bigger than or equal to 0. So, that is important. Okay. So, if I start the orbit at such a point, then v along that path remains bigger than this c. Okay. So, let me draw again a diagram. Okay. So, that is, so now I have this something. So, this is v of x equal to c, and I want to remain. So, this is just v of x bigger than or equal to c. So, that is the region and part of omega. Okay, everything is in part of omega. So, the orbit is confined to this region now, and that is what that estimate shows. Okay. Now, we would like to show that that orbit has to leave the epsilon ball at later stage. So, would want to show that for some, let me use t star positive, this x t star leaving the epsilon ball means this is bigger than equal. Want to show that. Okay. Assume the contrary again. Okay. So, this is just a sketch. You have to fill in the details using the simple analysis. Assume the contrary. That the orbit, the positive orbit starting at x 0 is contained in this x less than or equal to epsilon. Assume that. I already know that. So, we know that this orbit x 0 is already confined to this one. So, set of all x such that v x is bigger than or equal to c, and remember this is positive. Okay. So, in particular this is positive. Okay. And now we are assuming that the orbit is also contained in this ball. So, it is in the intersection. Okay. So, let me put some name for that. So, put k is equal to this set of all x such that mod x less than or equal to epsilon, and at the same time I want this c. Okay. So, by using continuity of v and this compactness of x epsilon, so you see that this is a compact set, and important thing is 0 does not belong to k, because v 0 is 0. Okay. v 0 is 0 because v 0 is 0. Okay. So, if I have forgotten that to include that thing, so include that v 0 is 0. Okay. That is always there, v 0 is. So, since it is positive there. So, 0 cannot be here. Okay. So, again by continuity, okay, so I will come to that later, and now you recall that hypothesis, and since now I am, so you see that hypothesis, the second hypothesis, that grad v dot f be positive definite in entire omega is not required. I am just applying only to this set. So, now grad v dot f is positive on K, and K being compact set, and this is 0 is not there. So, this, so let L be minimum of grad v dot f, and now you take x in K, and this is positive. Okay. Now, we are more or less done. So, again the same argument. So, then v of x t minus v of x 0, again this is equal to 0 to t. Okay. So, I am writing it again and again, so that you realize its usefulness, and now this is grad v dot f, and we are assuming that our orbit is restricted to K. So, this is in K for all t bigger than 0. So, that is important assumption. So, that this whatever value you are taking, now they are all in K, and in K. So, this is always bigger than or equal to L t. So, L is positive. Remember, L is the minimum of this grad v dot f. Okay. So, in particular, so this proves in particular limit v of x t at t tends to infinity is infinity. Okay. So, that does not say anything about the x t as of now, but now you see on this set x less than or equal to epsilon. So, this is a compact set in the Euclidean space R n, this is a compact set, and V is continuous, V is bounded. So, in particular V is bounded on K, because K is a subset of this, bounded on K. Okay. And so, if I call this, okay, but this contradicts star. A bounded function cannot have an infinite limit, this contradicts. Okay. Contradicts star. So, why this contradiction? The contradiction comes because we are assuming the orbit is restricted to, so the epsilon ball in this ball, we are assuming that thing, and to get this contradiction, therefore, so the orbit, therefore orbit cannot remain within this bound. So, now you again go back and see the definition of the instability, and this proves zero is unstable. Okay. So, you see that the question of stability or instability in this method of Lyapunov can be analyzed by the construction of suitable Lyapunov functions. Okay. So, again where are the examples? Okay, this we will discuss even in the next class. Okay. So, examples of positive definite function or negative definite function, because we have not seen any this far, and again these come from linear algebra. Okay, we will see in the next class. So, they come from linear algebra, quadratic forms. Okay. So, a quadratic form is of the form. So, this is V of, so in n variables x 1 x 2 x n. So, that is V of x is given by a I j x I x j. So, a I j are real and symmetric. Okay. So, these are termed as quadratic forms in n variables, and there are well defined necessary and sufficient condition for this V to be positive definite. So, there are necessary and sufficient conditions, necessary and sufficient conditions. So, these are, this is Sylvester's theorem in the theory of quadratic forms for V to be positive definite. Okay. So, we will discuss this. So, these are some important class of quadratic positive definite functions, and for a suitable for a given system we have to choose a suitable quadratic form. Of course, not all the time these quadratic forms will work. So, sometimes we have to even take higher order polynomials, but in many cases just these quadratic forms will suffice, and we will see some examples in the next class. Okay. So, we will discuss examples of positive definite functions, Lyapunov functions and other things in the next class. Thank you.